Here we are. It's the physics video lecture, psci 168, video lecture 19. Got a few things here on the table. We're starting a new topic, thermal physics, but I'm going to do review of what we've been talking about the last few weeks. But this time we really will launch into thermal physics. Got everything in front of me. Okay, so last time I ended with forest fires and discussion of fuel loads, excess fuel loads in the Sierra Nevada. So recall excess fuel in Sierra Nevada forests. Yeah, so I hope that interested you guys. That's something most people are not aware of. But we have these gigantic fires, and the fuel load is, maybe 5, 10, even more than that times what it should be. So that's why they burn so hot and so extensively. But since we were talking about fuel, right, I was trying to segue into thermal physics, and fuel represents a form of energy called chemical energy. Okay, so wood is fuel, and that is chemical energy. Now, in order to get there, in order to tie it together with all of our current energy concepts and understanding, it's going to take a little bit, but it's interesting material on the way. Before I get there, I'm going to do, like I just said, the review of the mechanical energy. So chemical energy versus what we've been studying, which has been mechanical energy. And the capacity to do work. So work is the very important concept here. And I'll show you how the science of physics that we've developed so far, which is actually referred to as mechanics, how it only depends upon length, mass, and time. Okay, so the units of mechanics. So we write this here. Mechanical energy. So mechanics, right? And that is a branch of physics. That's what we've been studying. And we have lengths, masses, and times. Everything we've done so far has been built up out of an understanding of length, mass, and time. So that's what I'm going to review. The unit of length is the meter, which we abbreviate with M. The unit of mass is the kilogram, which we abbreviate with kg. And the unit of time is the second, which we abbreviate with S. Okay. I'm only using one board today, so I can have a little more view of the table. So let's go over these here. So first of all, length. Length, the unit of length that we're using, we could use any one, but for consistency's sake, we use the meter. Okay. Everything that we've done in mechanics is formally built up with kilograms, meters, and seconds, and very convenient that way. Okay. So there's the unit of length is the meter. We also need to talk about area, right? That's a spatial dimension, that's meters squared, and volume is meters cubed. And if you've got that meter stick in front of you, you can construct either the length of area and the volume, meter squared, meter cubed. Now, as far as the volume is concerned, I want to mention something that I had not talked about before. Remember, we talked about the liter, and we have liter water bottles all the time. And that is 10 to the minus 3 meters cubed. Okay. So if you ever want to construct a meter, you take a liter, you take 1/10 of a meter on all three sides. Now, did I really just draw a 10-centimeter box? Pretty close. If I had really measured off, it would look about this big. Okay. So that's my attempted profile. So that cube holds 1 liter. And for example, if you pour water into it, you've got a liter of water in a cube that's 10 centimeters on a side. So that equals 0.1 meters, right? 10 centimeters is 0.1 meters cubed. And just for practice, let's write that out. If you're going to cube this thing here, you're cubing the 0.1 and you're cubing the meters. And so 0.1 cubed is 0.001, or 10 to the minus third, or 1/1000th, however you want to express it. And then you've got your meter cubed. I can leave it right there, okay? So yeah, I'm bringing this one up, of course, because the next thing we're going to talk about is mass. Okay. So we have length, areas, volumes. We need all of these. The liter in particular is 1/1000th of a cubic meter. I'll go ahead and even write that out. 1/1000th of a cubic meter. Good. So we're going to erase this now. Let's go ahead and go to point 2, which is mass. So our second quantity is mass. That's just the amount of a substance. I'm going to go ahead and use the letter capital M because I don't want to get mixed up with the meters. So we've got mass. Its unit is the kilogram. Remember the square brackets to ask what the units are. Its unit is the kilogram. And you can have any random chunk of metal or something else that might be a kilogram. So it's nice to know that the density of water, there's our Greek letter, and it's 1,000 kilograms per cubic meter, and therefore 1/1000th of a cubic meter is exactly 1 kilogram of water, if we're talking about water. Okay. So we've got the density of water, and we've got the mass of 1 liter of water. Mass of 1 liter of water. Because this way you can always, if you're out there reinventing civilization, you can always put together a kilogram as just a liter of water. Okay, so mass of 1 liter of water. We had that formula, mass equals density times volume, right out of the definition of density, by the way, because density is mass per volume. Mass per volume. So density times volume, we have 10 to the third kilograms per cubic meter. And the volume, of course, is that 1,000th, or 10 to the minus 3 cubic meters. Okay. And 10 to the 3 times 10 to the minus 3 is 1. 10 to the 0 is 1. Meters cubed cancel, so that is 1 kilogram. So you can say it many different ways, but it's something I want you to know. You've got that mass. You can always get a mass of 1 kilogram. You don't have to hunt around for a piece of metal or anything like that. Good, so that was, we had lengths, we had masses, and now we have time. The time is the second. And I'm just going to repeat so 3 time, and the unit of time is the second. Okay, good. You have a clock and you have seconds. But if you have a piece of string 1 meter long, or actually a piece of string of any length, you can build a pendulum and get your unit of time that way. So The simple pendulum consists of a small, dense object tied to the end of a string of length L. Turns out that the little mass that we put there at the end does not affect the time, and we let it swing back and forth. Okay, we let it swing back and forth. There's our pendulum. Period of the pendulum, T in seconds, is this. Period is equal to 2 pi square root of L divided by G. L is measured in meters. G is, so L in meters, G equals 9.8 meters per second squared. So there's a complete discussion right here. And we've worked on this before. But yeah, these 3 points, 1, 2, and 3, length, mass, and time, are the basis of all the physics we've done so far. And I've just given us practical definitions of all of them, so you feel confident about. And I'll remind you, if you wanted to time some natural process and you didn't have your watch with you, or you didn't have your phone or whatever you carry, if you had a piece of string, you could set up a little pendulum and just count how many beats occurred, and then you could measure the length of the string, do the calculation, okay, and figure out how long that physical process took. Okay, good. We'll leave that there. Kilograms, meters, seconds. Now I want to use those to remind us of all of our physical quantities that we've done all the way up into mechanical energy. So yeah, these 3 are the basis of mechanics, which is a branch of physics, and actually it's the foundation of physics. There's no other part of physics you can start with when you learn physics. You have to start with the mechanical basics that we've been doing. So let's call this physics, and I'll say parentheses, mechanics. So what were our physical concepts? Well, we actually did just have, as I've explained right here, length, mass, and time are the physical concepts, but I'll just go ahead and write length, mass, time, and repeat myself here, meters, kilograms, seconds. But then what else did we have? We had, for motion, we had, in addition to position, which would have just been a length, okay, so I'll write here position and displacement and velocity and acceleration. So these were our concepts of motion. Acceleration, okay, position, displacement, velocity, acceleration. X had the units of meters. Delta X also had the unit of length, which is a meter. Velocity V equals delta X divided by delta T. So that was meters per second, and acceleration A was delta V over delta T, change of velocity over time. So that was meters per second, so that's meters per second squared. Okay. So we're talking about motion, that's all lengths and times. Then from motion, which is also referred to as kinematics, we go to dynamics. So dynamics, and here we have Newton's law. Force is equal to mass times acceleration. That's the first time the mass came in. Pardon the M's here. Right now this is a mass in kilograms. And the units here are, on the one hand, they are newtons, But then we learned that newtons is kilogram, right? We started with newtons, okay? But due to this law right here, kilograms meters per second squared. Okay? So the newton is not an independent unit, although one can start that way, but when you actually have the science of dynamics, newton is kilograms meters per second squared. Okay? Kilograms times meters per second squared. And then we have work. I'm going to write this out. This is the most important one. Okay? Or the culmination of it all, because this is energy. Okay? So for work, let's go ahead and write this out. We know it was a force times a displacement, F delta X, because we were just lifting a weight originally. So we have F delta X, that's newtons times meters. We call that a joule. Okay. So newtons times meters is joules, but of course, what is that? That's kilograms meters per second squared times meters. But how about if I go this way, kilograms times meters per second squared, because I have meters times meters, that's meters squared and second squared. And that is mass times velocity, which of course is the unit of the kinetic energy. See how all this stuff just fits together. Okay. And energy of motion. So here we have work, and energy and potential energy, capacity to do work, and over here we have motion. So energy of motion, and over here energy of position. So I could actually write, we have potential energy, which is work here, energy of position, and then we have kinetic energy, energy of motion. I'm going to write that down. Potential, I've been calling it stored work, but stored work or energy of position. Right? When I say position, I mean, for example, the water in the reservoir, it's above the powerhouse. Okay, it's stored work, but it's energy of position. And over here we have energy of motion. So this is what we've done so far. Okay? And it culminated in the hydropower discussion. And if you understood everything we've done so far, you already know a lot. The next thing we have to do, like I said, is go from mechanics and mechanical energy. All of this has been mechanical energy, this entire discussion. So yeah, I'll even write this here, mechanical energy. So we have to go now to thermal energy. Energy, for example, that is contained in fuels. Now, that's going to take us a little while, but like I said, we're going to build it up just as systematically as we build up mechanics, with some really basic concepts, and then we have a chance to really understand it. Okay, good. So, how much time did this take? We've got nothing but time. Fantastic. All right. So, next is thermal physics, on the way to understanding thermal energy. And I had on the board last time the basic point from which we're going to start, hot and cold, just what you feel on your skin. So once again, we'll title this Thermal Physics, and we'll start with the sensation of hot and cold. So thermal physics. And like to number things, so point 1 here is we just have the sensation of hot versus cold. Okay. And even with these sensations, there's interesting things you can do. short of burning yourself or something. But you can put one hand under really hot water as much as you can take, and then put one hand under really cool water, and then put them both under lukewarm water, and you get interesting investigations of sensations and relative heat and things like that. So those things are kind of fun to do, but I'll just go straight to the idea that we're going to associate hot with fire and its application to things. We could use fire to boil some water, and cold would be really cold water or frozen water, which is ice. And we can cool things down by applying ice to them. So we have fire versus ice, and that's associated with all of our sensations of hot and cold. Or with not all of them, but with many of them. Many of them. Good, so I brought a torch to represent fire here. And it works. This is a real flame. Okay. And the next thing I want to do, I didn't bring a bucket of ice, I can do that next time. I want to, beyond the sensation, I want to talk about some associated phenomena. Aside from us burning ourselves or any other things, burning things, an interesting phenomenon is applying a flame to some carefully sized pieces of metal. Hope these two go together. Okay, so what I have here is a ring, and I have a ball that barely passes through the ring. Actually, it passes through comfortably, but if you look at it closely, I don't know how much you guys can see, but there's very, very little gap. Okay, so it's pretty well machined here. And what I'm going to do is just apply heat to this ball. The ball and ring are both made out of brass. I have to heat soak this for a minute. This is just a regular propane canister. So nothing fancy here. A little bit hotter. And that does the trick. The ball, you can't see any size difference, but it no longer passes through the ring. Okay, so that's the phenomenon I'm talking about, is called thermal expansion. Okay, so this is a good demo actually, because even if you took a ruler, you wouldn't be able to tell the difference, but it did expand in a very controlled manner. The related demo that I hope works. So now we have the opposite situation. We have a ball that won't pass through a certain ring here. So I'm going to heat this ring, and what's interesting here is you can imagine the thing expanding so that it's like an inner tube, in which case the inside would even get smaller and the outside larger. Or the expansion could be along the entire dimensions. So this one I'm going to heat soak. However long it takes. Fantastic. Okay, so now this one does pass through. So the dimensions of this expanded uniformly. It didn't get smaller in the middle and bigger on the outside. So that's another example of thermal expansion. This one's kind of dangerous. If I leave this in here long enough, it will shrink onto the ball again and clamp it down, and you really won't be able to remove it. Because then you try to heat it and they both expand. So good. Those are some important thermal expansion demonstrations. So, thermal expansion. And we had one demonstration, ball and ring. Yeah, you can get a little picture of that or whatever it takes. Right. There's the handle. One of these is the ring. The other handle. And one of these is the solid. Okay, so we have that. Another interesting thermal expansion demo is just this thin piece of metal, which doesn't look like anything special. Okay, it's got a handle on it. If I apply heat to it, it bends. So this is actually technologically used to be more important than it is right now, because it used to be used in thermostats. If you're in an old apartment where they haven't changed out the thermostats yet and you pull the cover off, you may see some some thin metallic strip that's coiled up. And what this is, so my second demo, it's called a bimetallic strip. Bimetallic strip. And what we have here, I'll do the expanded view of it. We've got the handle, and the metallic strip is actually, even though it's very thin, it's two different metals that are fused together. Okay. They're not red and black, but they are in this picture, okay? So we have two different metals, and what happened here is one of them expands more than the other, and therefore it pushed it over, curved it, okay? So one expands more than the other. In the case of my picture, if black expands more than red, then it curves over to here. Like that. So bimetallic strip, one metal expands more than the other. And already with this, with this phenomenon of thermal expansion here, with this phenomenon, we're ready to make a thermometer. Because all we would have to do is put a scale here, and this would be hot as a flame, and this would be the room temperature. Now, I haven't shown you that it'll curve in the opposite direction under really cold temperatures. I'll have to bring some liquid nitrogen in, and I can demonstrate that to you later. Okay. So we go from the sensation to some associated phenomena. This was with fire. And we get the thermal expansion. Here's an application. And so we're now ready to talk about thermometers. And I just gave you an example. But this was pretty crude, right? We have hot and we have room temperature. So we also need temperature scales. So thermometers and temperature scales. That's our next topic. Okay, checking the time once again. Good. So remembering these things, thermometers and temperature scales. So I brought another kind of thermometer. This is a traditional mercury thermometer. And it's you're not going to see this from this distance, but there is mercury in here, and it expands under increased temperature, and then it goes up the capillary. I'm going to draw a picture of that, but if I had a bucket of, a bucket of ice in here, and then I were to put this thermometer in there for a while, it would register at a certain level on my thermometer, and I could level that temperature that ice, let's say I had ice water, temperature that ice melts. And then I could put it in this thing with boiling water in it, and then the column would go up higher, and then I would label that temperature that water boils. Okay, so that's the idea that I'm going to present now up here on the board. So thermometers, we have thermal expansion. So the thermometer that I want to just draw for us, so we have a nice cartoon here. So it's a long capillary. It's got a bulb on the bottom, or a reservoir. And I'm going to draw two of them right away. Got a bulb on the bottom, and it's a long, thin capillary. And it's filled with something that expands. So you have thermal expansion. I'll make it red here. I'll have one that goes here, and I'll have one red column that goes up to here. Okay, make those thick enough. So these are our thermometers that are working directly. Oops, that one doesn't have to go that high. Just wanted to make it a little thicker. Okay. Goes right up to there. And there's our capillary. Okay. So I'm going to let this be ice melting. So ice melts at this level here. And up here I'm going to have water boils at this level here. Okay. And then we just make a scale and maybe make a different scale here. So suppose we let ice melt at 32 and up here 212, then this would be the Fahrenheit scale. It's Fahrenheit. On the other hand, if we call this, I see I did the relative distances, forget it, relative separation there. If we call this 0 degrees and this 100 degrees, then this is the Celsius scale. Okay, so Celsius, and this over here is Fahrenheit. You can see by this construction you could have any number of scales. You could have as many scales as there are names in the telephone book. But these are the common ones we're aware of. And in particular, this one we're using in physics with the rest of our established units. Okay, so in physics we'll be using the Celsius scale. So temperature conversions are somewhat interesting. And I'll just do a little section on temperature conversions. I'm still numbering this stuff. Is this 4? Temperature conversions. Of course, you can just type it in to a search engine or a computer and get any number of temperature conversions that you want. But it's good to know a few. So leave a little room in your notes and then go ahead and look these up and put them in real quickly. So you want degrees Fahrenheit and degrees Celsius. Let's say body temperature would be 1. Room temperature, which of course is a range of temperatures, but that'd be another thing that would be good to know. Body temperature, room temperature, and some cooking temperatures, some baking temperatures. Maybe put a couple in. Combustion of paper. remember there's a book we all used to read in high school called Fahrenheit 451, which I think is the combustion temperature of paper. Look it up. Okay. And so you have a handful of these, and you have them in Fahrenheit, and you just look up a conversion in Celsius as well. Okay. So what I want to do as well is show you how we would derive, how we would figure out the conversion if we had to, just based on these data right here. So if we made a graph in which we put degrees Celsius on one scale and degrees Fahrenheit on the other, we have these two common points. So we have ice melting at 32, which is the same as 0. So we have a 0 here. I think it'll be a more clear graph if I reverse this. It doesn't really matter, okay? Fahrenheit, degrees Celsius. So once again, so ice melts at 32, so we'll call this 32. And on the Celsius scale, we have a 0 here. So there's a point on our graph. And then we have water boiling, which we'll call 212 right here. And that will be 100 on our graph, okay? So that would be a point over here. And then the conversion is just always the points along this line. Okay. But those of you who remember some algebra, we could use the point slope formula. So we could say degrees Fahrenheit equals 32 plus the slope here, which is 212 minus 32, which is 180, right? 212 minus 32 is 180, divided by 100 minus 0, which is 100, times our temperature in degrees Celsius, which I'm going to write that way. Okay. And then we would just have to solve for this. So for example, we'd have degrees Fahrenheit equals 32 plus 18 tenths, and 18 tenths is 9/5 times our quantity in degrees Celsius. And here I'll use a different color, but we can get the two formulas that way. So we have the temperature in degrees Fahrenheit is what I just wrote here. I'm going to write it 9/5 times the temperature in degrees Celsius plus 32. That's one formula. And the other formula would just reverse this. We have, I have room right here, yeah. Temperature in degrees Celsius. Right, we've been doing enough of this algebra all semester. Temperature in degrees Celsius is 5/9 times the temperature in degrees Fahrenheit minus 32. Okay. So those would be your conversion formulas. Of course, you just look them up in a computer as well. Good, so that's our temperature conversion topic. Now there's one more temperature scale that you may have heard of before, the Kelvin scale. That's going to take a little bit of motivation. It's an important one as well. That we're going to make use of. We're going to make use of degrees Celsius, and then we'll also make use of Kelvin. Checking our time. Okay. This is almost a good place to stop because the entire discussion is going to take a little longer, but I will show you what we're going to talk about next. So I'll introduce this and then we'll do the analysis next time. So this here is a mock-up and of a sort of thermometer. Actually, it's a multi-purpose device. So let me just describe what we have here. We've got a beaker with air. Okay, it's just air inside. It's connected by a tube to this vessel that has some red colored water or something. goes up here, and up here at the top, this is open to the atmosphere. Okay. Open to the atmosphere. And what I can do is, if I'm patient, I can heat up the air in here. Hey, I don't even have to be that patient. So yeah, the red column of water is actually moving along there. I was about to be impatient and blast it with my torch, and I think I still will. Okay. So you can see, apparently I've warmed the air in there. In case you don't believe it, a little torch action here. Make sure nothing goes wrong, right? There we go. Excellent. So this is a form of thermometer. We could also have some kind of scale, just like here we got some kind of scale on this. Apparently the application of heat raises this column of fluid, which already came back down. Okay, that's fine. So this is a gas thermometer. It actually also does other things, because this open tube here, if I blow past it, it'll change the pressure inside as well. Maybe I'll just do that. Well, can't see it at the same time. Maybe you guys saw that. Be that as it may, for us this is a gas thermometer, and our idea, too hot there, our idea that we're going to pursue next time is if we were to put, say, boiling water in here, and this thermometer would tell us, you know, the temperature, or ice water, and the thermometer would tell us the temperature, and then we would compare these temperatures to the height of that column. So gas thermometer is next, and until then, I guess all we have today in terms of homework is just to make sure to incorporate some of this into your notes. You know, if you want to use these formulas or investigate or repeat this derivation on your own, that's also useful. Good, so next time, the gas thermometer, the Kelvin scale, and other good things. Okay, see you next time.